Okay, in last video we talked about the counting sort, and counting sort is not a comparison based sorting algorithm, so we are able to beat the n log n. And let's move on and talk about another linear time sorting algorithm. And let me start this by showing you this card. So what is this? Probably you have never seen this before, and you may assume that this is kind of similar to a scantron, right? But well, even for the modern time scantron, it doesn't really require you to punch holes, and so this is something really old. And well, related to this, and there's a story. And how did IBM got big originally? And IBM created the reader for this kind of punch card. So this the punch card reader can scan and sort this kind of a punch card for the census data. And this is really old, more than 100 years old. And if you have never seen this, and that's fine. And probably even if you ask your grandpa, and your grandpas may not see that, have seen that too. Okay, well, anyhow, our question starts from this kind of punch card. So for each of the punch card and for each of the column, there are a total of 12 places could be punched. And as you can see, for each of the column, there are the digits from 0 to 9, so 10 digits, and then above them, and there are two other places can be punched. So for each of the column, there are 12 possible places could be punched. And then we want to sort the information, and so that we can put the cards into the separate bins. And the problem that we have to deal with is for the card reader, it can only touch one column at one time. Okay, so if we are trying to sort those cards, and then we have to sort one column at one time. Okay, so the similar idea brings us to the Radix sort. So for Radix sort, and we are sorting the numbers. But other than sorting, instead of sorting the values as a whole number, for example, 124, and then instead of sorting the values as 124, we are sorting three digits. We are sorting 1, and then 2, and then the 4. Okay, we are treating the 124 into three separate digits, and then we are putting all the numbers under using the same number of the digits together. In this case, it will be 3. So we are putting all the numbers of 3 digits together, and then we are sort all those numbers digit by digit. Okay, so when we are doing the Radix sort, we have the array A, that's the input array of the values, and then we are assuming again all the values are integer numbers. And then we also specify the D, and the D says how many digits are there in all the values in the array A. Okay, so that's again a very strong assumption. So if the D is 3, this means that for all the values in the array A, there are 3 and only 3 digits in each of them. And then how do we do the sorting? Well, from 1 to the D, well, we are doing a stable sort only on that specific digit. Okay, so let's see such an example. So if we want to sort those values, and then we are going to start from the last digit, or we are starting from the least significant digit, and then we move on, and the last pass we want to sort the most significant digit. Oh, where's my pen? Okay, here it is. So if we want to do a stable sort on the last digit, so we are only touching the 9, 7, 7, 9, 6, 0, and 5. Okay, so what is, come on, what is the result? The result will be, okay, the 0 first, so 7, 20, 0. And then after 0, we have only one 5, so 3, 55, and then after that we have a 6, so 4 36, and then we have 7s, 4 57, 6 57, and then we have 2 9s, so we have 3 29, and then we have 8 39. Okay, so remember we are doing the stable sorting, so well we have to do the 3 39 first and then 8 39. Okay, so I'm going to check all of them. So the last digit has been have been sorted. So we move on and we want to sort the middle digit. So for the middle digit, we are touching the 2, 5, 3, 5, 5, 2, and 3. Okay, so we are doing the 2, 20, 0, and then we have the 3, 29, and after that we have a 3, 4 36, and after that we have, oops, I think I missed this one, so 8 39, and then we have a bunch of 5s, so 3 55, 4 57, and then 6 57. Okay, so the middle digits are sorted, and the last pass we want to sort the most significant digit. So we are touching 7 3 4 8 3 4 and 6. So the smallest value would be 3. So 3 29, and then we have another 3 3 55, and then we have 4 4 36, and then 4 57, and after 4 we have 4 we have 6. Okay, we have 6 57, and then 7 20, and then 8 39. Okay, so this is the sorting process, and then we just sort digit by digit. And the cool thing is for each of the digits, there are only up to 10 values. So, well, the sorting will be easy, and then we sort from the least significant value or the least significant digit up to the most significant digit, and then our sorting will be done. Okay. So, and the next question we want to say is, how do we prove that the Radix sort is a valid sorting algorithm? So we have to assume that for the lower order digits or the less significant digits are all sorted, and then we are touching the current digit at the position I. And then there are when we have two values, and then there are, if you're comparing two values and there are two possibilities, and if those two digits on the position I are different, and then we are and the position I or the digit I is so far the most significant digit to be sorted. So whichever is lower will be put the first. So in this case, we are still having a valid sorting so far from the digit I and then all the lower order digits. Okay, and then another case will be if on the position I we have two values, and on the position I those two digits are the same. And then remember, we are doing a stable sorting, and the stable sorting means that even for the digit I, those two values are the same, but on the lower order digits, whichever is smaller will come up first. So in this case, well, we don't break anything. So far on the digit I, it doesn't matter that those two values have the same digit on the digit I or not. We can prove that so far we have been doing a safe job in sorting all the values using using the Radix sort. Okay, so this is how we can prove that the correctness of the Radix sort. And then, well, let's talk about the time complexity. So, before we do that, we want to go back here, and then what is the stable sorting algorithm do we want to use? And I think, well, the counting sort could be an easy answer. And then if we are using the counting sort, and then we have the from we have n numbers, and then the range will be from 1 to k. So the time will be O n plus k, right? And then in the Radix sort, we also have a d, and the d means how many digits are we sorting in the list of A. And just now, when we did this example, and you will see for all the numbers to be sorted, and there are 3 digits. So in this case, the D will be a 3, saying for all the numbers to be sorted, there are 3 digits. So we are going to run the Radix sort for 3 passes. So we are going to multiply a d to here. So we are going to have a ODN plus ODK. And then, well, usually we assume that for the d, that is a constant, and for the k, that is the ON. So we can still say the Radix sort, that is a ON time algorithm. So it seems that that's cool, right? And especially if we are trying to sort a big range of the values, and then we can use the Radix sort. And the trick will be, say if we are doing the 64-bit numbers, and instead of doing a brute force way of a counting sort, we can break the 64-bit into a 4-digit of the Radix sort, and then for each of the paths, and then we are only sorting the 2 power 16. So this will help us to reduce the k value of the counting sort. So instead of having the k value to be 2 power 16, now we have the k value to be 2 power 16. So that is much better. So if we are doing if we are sorting 1 million of the 16 bits of the integer numbers, and then using the Radix sort will be much better than using the counting sort. So, and the question is, why do we not use Radix sort a lot? So think about this. And there are a couple of the issues. And, well, let me ask you this. For the quick sort, do we put in any assumption? Well, no, right? We can sort integer numbers, we can sort the numbers with different number of the digits, and we can sort a mix of the integer numbers and the float numbers. So, well, for the quick sort, there's no constraint or limitation. Well, and for how about the Radix sort? For the Radix sort, we have to put in some very strong assumption to use the Radix sort. So this means the Radix sort is not really a general purpose sorting algorithm. Okay, and then what else? Well, for the Radix sort, is that a sorting in place algorithm? Well, in the Radix sort, remember we are using the counting sort, and for the counting sort, we need the additional memory space to create the B and the C, right? So we are not just sorting in place of A, because we also want to create the C, and then eventually we are building a new list of the B, and then we put all the values in the B instead of at the original array of A. So, well, Radix sort is not a sorting in place algorithm. Okay, so, well, if we want to review what we have learned about the Radix sort, it is indeed a fast algorithm, and then it is ON. It's simple to code, but it doesn't sort in place. And plus, the worst thing about the Radix sort is that it's not a general purpose sorting algorithm. Okay, well, and for this, after this lecture, and you want to read the textbook section 8.1 to 8.3, and in the next class, eventually we want to move on to something else other than sorting algorithm. We are talking about the median and the other statistics. Okay, so that's it for today, and I will see you in the next class. Bye bye.